Hello everyone, welcome to the module on stereochemistry. We are still trying to discuss the arrangement of atoms in space and look at how does that give rise to different properties. In this lecture, we will go into a bit in detail about what are the symmetry elements of a molecule and how that dictates the chirality or the lack of it in a molecule. Before we get there, let us just quickly recap what we learned in the last lecture. In the last lecture, we had seen different kinds of isomers, that is constitutional and stereoisomers. By constitutional, we learned that here to go from one form of isomer to another, one has to break a bond and rearrange the atoms, and that would give rise to constitutional isomers. That is, the connectivity for a constitutional isomers are completely different. A classic example we had seen was between a cyclohexane and a few forms of hexene, 1-hexene, 3-hexene or others. On the other hand, if you come to the stereoisomers, here the main distinction is the connectivity remains the same, but the way they are arranged in the space is what distinguishes the two isomers. And for this we had looked at two classes. One is called as cis-trans isomers, and we had looked at few examples of those, and another is what are called as isomers based on a chiral center or an asymmetric center. So, in this lecture we are going to go into a bit more detail on that and see what are the different properties of that system. We had also learnt that there are two different kinds called as conformations and configurations. In conformations, you have different isomers which actually can rapidly or can be easily interconverted between the two without actually breaking the bond. However, in case of configurations, one has to break a bond to go from one configuration to the other configuration. And an example we saw were the two chiral forms of a particular molecule called 2-methyl-butanol. And we had also discussed in a bit detail about cis-trans isomers. So, with this background, let us now get into looking at a bit more closely on stereoisomers which have a chiral center or an asymmetric center. So, these are the two examples which we had looked at in the previous class. On the left hand side, you have a 2-methyl-butanol derivative in which the methyl group is protruding out of the plane of the screen. On the right, you have the methyl actually going back, and I am sure you are all aware of what is called as a Kahn-Ingold Prelog method of naming this or giving them the absolute configuration, that is the R and the S. So, just to refresh our memories, let us just look at that. If you go by the Kahn-Ingold Prelog method, so then if you know, we are looking at this particular carbon atom here, and so then what you have is you are going to try and look at the priority of the carbon atoms. So, we have one, this would be the first priority because that has the oxygen attached to it. Then you have the second priority is this, which is having two carbon atoms, and then the third priority would be to the methyl, and you would also have something which is going back, which is the hydrogen, correct. So, if I put it here like this, so in the Kahn-Ingold Prelog we have the hydrogen always pointing away from us, and that is indeed the case in this particular isomer. So, if you now put it like this, we have 1, we have 2 and 3 arranged in space. So, then this would actually go as a clockwise, and this would give rise to R enantiomer or R form, and that is what we have here. Similarly, one can elucidate for the one on the right hand side, and this we would call it a S enantiomer or the S configuration, correct. And this is what we typically saw as in a molecular model we saw as this, where a central carbon atom is attached with 4 different units, and this was also the definition or the proposition given by Van 't Hoff to begin with. Now let us look at one particular statement and see if this particular definition that a carbon attached to 4 different substituents is chiral, is this true or is this universal, or are there any limitations on this particular statement? To understand that, let us go back and look at a very classic example of a system which contains 2 centers or 2 chiral centers. Here is an example of what is called as a tartaric acid. This was the first derivative which was studied by Pasteur in 1850s, around 1850s, and what he observed is that there are 2 forms. One is called as the one form which rotates the plane of polarized light along one direction, and that is why we call it as optically active, because it rotates the plane of polarized light. And similarly, there is another form which actually rotates on the opposite direction. So these were the 2 forms which Pasteur understood or Pasteur isolated. However, there was also another form which was later realized that this was actually optically inactive. That means if you shine a polarized light on it, it would not absorb or it would not change the direction of the plane polarized light. So this was a bit puzzling. If you now look at this particular molecule which is shown here, in the light of what we just discussed above, what you indeed see is that it has what we call as chiral centers. It has 1 and 2 chiral centers, but still it is actually optically inactive. So how do we go about rationalizing or understanding this? And this is not just one particular molecule. There are actually many such systems where you could have chiral centers in the 1-2 positions which would be optically inactive, and there are also different kinds of molecules called as allenes which do not even contain a chiral center and they are still optically active. So how does one rationalize or understand this? So we need a much more broader perspective on this. In order to evolve a broader perspective, what we need to do is we need to go back and look at symmetry and chirality in relationship with each other. So far what we said was, we just said that if you have a carbon atom attached to 4 different centers, then we call it as a chiral center or a molecule as chiral. However, when one has more than 1 carbon atoms or more than 1 chiral centers, then the whole system has to be considered in totality. So for that we have to actually understand what are the symmetry elements or symmetry operations which are applicable on a molecule and how that leads to chirality or the lack of it. There are 4 major or 4 classes of symmetry operations which are possible on a molecule. One is called as a proper axis and proper axis of symmetry, and the other one is called a reflection or a symmetry plane, and third is called the inversion center, and the fourth is called as the improper axis. So now what we will do is we shall look at each one of them in a little more detail and try to understand them with a few examples. And finally we will come back to what is the relationship between these elements and chirality of a given molecule or a system. Let us begin by looking at what is called as a proper axis of symmetry, which is denoted by this C with an underscore n, and this is simply nothing but the axis along which if I rotate the molecule, it should come back to the same position, and the number of the turns which it would take is what is denoted as n here. It would become clear if I take you a simple example of a molecule of water. If I take a molecule of water which is shown here with the red oxygen and the 2 white as the hydrogens, and if in order to get back to the same molecule or an indistinguishable molecule, what I have to do is along this direction, along the direction perpendicular to the oxygen, I would rotate it by 180 degrees. I would go and rotate it by 180 degrees. That would lead me to the same molecule again, right? And here what n stands for is 2, because I need to rotate the molecule along this axis by 180 degrees to get back the same molecule. So, if you put n is equal to 2 in the formula, you would see that I need a 180 degree rotation, and that is indeed what we did here. We went from a molecule like this, we just rotated by 180 degrees to get the same molecule back. I hope this gives you an idea of what I mean by a proper axis of symmetry. To give you another simpler example, so I have taken here an ammonia molecule NH3, where the black ball represents the nitrogen and the green ones represent the hydrogen in this case. If I have to get back this molecule, I need to do a 120 degree rotation, that is, this is the angle by which I need to rotate, which is the 120 degrees. So, if I rotate, then I would get back the same molecule, and I can keep on doing this to get the same molecule. And if you now have divide the 360 degrees by 120 degrees, that is the angle needed to get back to an indistinguishable molecule, you will now see that we have a C3 symmetry. That is what is written here. Now, let us go ahead and take a look at a slightly difficult but still a simple molecule, which is called as an ethane, which is something which we looked at in the first 2 lectures. So, here I am showing you a staggered configuration of an ethane molecule, where you see the 3 hydrogens which are actually coming towards you and a carbon, and at the back we have 1 carbon and the 3 hydrogens, correct. So, I guess this would be again very apparent if you want to look at what are the symmetry elements present. So, the one way to do is to hold this carbon and rotate the entire molecule by 120 degrees and see if I get a similar molecule back. So, let us do that. I am going to hold this carbon and I shall just rotate it till I get it back onto this position, that is a 120. So, you see that I have got exactly the same molecule back. If I hold any one of them and rotate, I would get back the same molecule. This is actually very similar to what you saw for the ammonia case, that because these 3 are in a predisposition along the tetrahedral of a carbon, you will have a C3 symmetry in this case, which is, I guess, is little more obvious. However, what is not obvious is the C2 axis. So, to understand the C2 axis, let us do one thing. Let us now hold the molecule like this, where what you see is that I hope you all can see that there is one particular plane which is going through this hydrogen, the carbon and the hydrogen. So, the plane which is actually going through these 4 atoms is one plane, correct. And if I have this particular plane, what I can do is I am just going to hold this and I can come with an axis which is perpendicular to this, and I will try to do a 180 degree rotation here. So, I will around this, if I do a 180 degree rotation, I actually end up on the same molecule. I hope you see that and I can just do that again. So, the hydrogen is on the bottom is coming towards you, and the hydrogen at the back is coming towards me. And if I do again a 120 degree rotation, a 180 degree rotation or a C2, you would see that the same molecule is retained. That is, the bottom hydrogen is again coming out of the plane and towards you, and the one here at the top carbon is coming towards me. So, this is what would give rise to a C2 symmetry, and since I can create one plane, I have one C2 symmetry which I am showing you currently, but I can, since there are I can actually similarly make 3 total planes where 2 hydrogens and 2 carbons are present. Like for example, this is one plane which I have currently now, and what I can also do is I can also take these atoms, which is again another plane, and similarly you can also come up with another, which is this. So, it may not be very apparent now because all the substituents are exactly the same. So, it will be hard to see all the 3 planes and the consequent C2s, but I hope you at least can see one of the planes and the C2 axis which is perpendicular to it or the orthogonal to it. Alright, now let us go ahead and look at a slightly more symmetric or a complicated system. So, here what we have is we have a benzene as a particular system, and I guess this is a little more easier to look at because the molecule is planar. So, you can actually just look at it in the plane of the board itself, and here what you have is you have a different elements of symmetry. One is you can do what is called, if you actually go orthogonal to the bolt, that is perpendicular to the bolt, have a, I will just try and so if I draw the benzene again here, assume it is symmetrical or the bond lengths are the same, I can actually come up with an axis which is, or the axis is perpendicular to the plane of the screen. So, if I come up with this, then what I can do is, so if I rotate it by 60 degrees, that is 1 carbon to 2, so then I would end up in the same molecule again, right. So, the degree of rotation I am doing is 60 degrees. So, that means 360 by 60, that I have a C6 axis of symmetry in this case, correct. So, that is one of the elements which is shown here, that is the C6. Similarly, I can also do a 120 degrees, that is if I draw this, and so then I would do a 120 degree rotation. So, if I now do a 120 degree rotation with the axis perpendicular to the plane of the benzene, then I would again get the same molecule, and if you now divide 360 by 120, you would get a C3 symmetry, correct, because now the n is 3. So, that is what we are looking at here is C3. So, we understood hopefully C6 as well as C3. And now coming to the, so these were actually where the axis was perpendicular to the screen of the or the plane of the benzene. So, now let us come back and look at what is called as the C2. So, in this particular case you can, so you can try and do one thing, which is now you are going to try and look at within the plane of the benzene. So, for that I will draw again once again, so that it is a bit more clear. So, now what you can do is you can actually have a plane which is passing through this. If you now along this plane which is within the plane of the benzene, if you now flip it, you would get back the same molecule, right, because the molecule is symmetric. So, now you get one C2. Similarly, I guess you can easily understand that I can get this C2 and I can also get this C2. So, I already have 3 C2s now, and so this is when you go from one atom to the other atom, that is this to this or similarly to the other atoms. Now, what happens if I go between the atoms? So, let us look at that in a. So, since the bond lengths are same, although I am drawing double bonds here, but this is actually alternating double bonds. So, the bond lengths are exactly the same. So, given that, what I can do is I can actually go in between the two bonds as well. So, this is where I am actually going through the not going through atoms, but I am going through bonds, and this would also give me one C2 axis. Similarly, I can have 2 more C2 axes. So, what this tells you is that you can have symmetry elements or the symmetry operations going through not just bonds, you can also have them going through atoms as well as through the bonds. Alright, so now we looked at what is called as a proper axis of symmetry, and now let us go ahead and look at something what is called as a plane of symmetry or a reflection plane. So, in this what we will do is we will actually take the molecule and look at the reflection, if there is any reflection in the molecule, and on reflection does it give a same molecule or a different molecule. So, I understand that these symmetry operations which I am trying to show now are actually not that easy to understand if you do not have these kind of molecular models with you, But what you can certainly do is you can go to this very nice website which is given here, symmetry@OtterBind. So this has very visual ways of looking at symmetry elements and symmetry operations in these simple molecules and even in some of the more complicated systems. I think that would give you a much more better feel of what these symmetry elements are. So I would encourage you to go back and play around on this website. Coming back to symmetry plane, so now let us again go back to a simple case which we looked at, that is the molecule of water. So if I take this molecule, so is there any reflection plane or a plane which cuts the molecule equally? So there are actually two symmetry planes here. One, if I take this molecule and if I cut it in this, or if I put a plane across this, I see that the atoms on either side are exactly the same. That is, if I put a plane here, I have a hydrogen here and I have a hydrogen on the other side. So that means I have one plane of symmetry or one sigma plane here. And what could be the other sigma plane here? Because this is a little obvious, the one which I showed you is obvious. So the other one is actually I could even cut through the atoms, right? I can actually, in the plane of the molecule itself, in the plane of water molecule, if I cut or if I have a plane which is going through the atoms, then that would also give me a sigma plane. And so in totality I have two sigma planes for a simple water molecule. I hope that is understandable. And now let us look at the case of the ammonia which we had previously seen. So if you now take this molecule, again I am viewing it from this side, from the front on view, I could have one sigma plane which is actually going through the carbon and one of the hydrogens. And here what you see is that if I have a sigma plane going through, it has both hydrogens on the other sides. So that means it is a symmetric system. So this would be one sigma plane, and similarly I can have it going through the other two as well. So in total in ammonia I would have 3 sigma planes. And now coming to our more symmetric benzene molecule. So you would have imagined or you would have already guessed that here also similar thing is possible. So let us just look at that briefly. So if I draw again on one more benzene for the to make it clear. So I could have a plane which is actually, we could have a sigma plane which is going through this and perpendicular to the plane of the benzene, and that would be one sigma plane. And similarly I could draw two more here, one and another one. So I have now 3 sigma planes which are actually going perpendicular and through the atoms, right. And similarly as we did for the proper axis, we can also do for the sigma plane, that I can draw now between the atoms and through the bonds. So yeah, I can actually have one which is going through this, and similarly between these two opposite bonds I can have another going through, and here again I have one more going through this. So this is 3 sigmas through the bonds and 3 sigmas were through the atoms, right, and these are little more sort of intuitive. Whereas another one which people typically miss is that if I have a benzene, I can also I can also slice through it, or I can also have a plane going across the atoms, and that would also give me a sigma. So in total I will have 7, that is one is the horizontal and the other 6 are vertical. Among the 6, 3 are going through the atoms and 3 are going through the bonds. So you could actually play around with this. You can draw the molecule on a sheet of paper or go through this website and play around, and I am sure that will become a little more clearer to you as you go through that website. Now let us go ahead and try to look at what is called as an inversion symmetry. So an inversion symmetry is one in which every atom should have a corresponding atom at exactly the opposite distance in the molecule. So this might look a bit mathematical and abstract. So to clarify that, let us look at a case of the benzene. Again, if we take the benzene, and what we have here is that we have a center of inversion here, and here I will draw the hydrogens just to be point out. And now if I want to go from here to this carbon, I am going to draw here in this direction, and to see whether this is indeed the center of inversion I need to come back equal distance and I indeed find another carbon. Similarly, if I want to go towards an hydrogen, I can go towards this hydrogen, and to find out whether it is again a center of inversion, I need to come back and find another hydrogen here, and I have a hydrogen here as well. So, you can do the same exercise for all different kinds of atoms present in the molecule, and that would lead you to a center of inversion in benzene, which is at the centroid of this hexagon. And another let us look at another example, which is this 1,2-dichloro-dibromoethane. So, here I have a model of this 1,2-dichloro-dibromoethane for you. So, what I have is the black ones are the carbons, and the green ones are the chlorines, and the orange ones are the bromines, and the white ones are the hydrogens, correct. So, what I am trying to do is I am going to hold it like this, let us say I am going to hold it like this, and let us say I have a center of inversion right in the middle of this bond, and if I have that, then let us go from here to the carbon atom or to the hydrogen atom. I see that there is I can find a hydrogen atom, and if I actually go back from here to on the reverse direction, I indeed see a hydrogen atom here, right. So, I have both hydrogens on this positive as well as the negative side. Similarly, if you want to do for the chlorine, you do see that from here going from center, I can go and find the chlorine atom here, and if I come back, I do find a chlorine atom, and the same thing holds for the bromine atom as well. So, this would tell you that the molecule has a center of inversion, which is again another important symmetry element. And finally, we will come to an important thing which is called as improper axis of symmetry, which is nothing but rotation by 360 degrees by n, which is the proper axis of symmetry which we saw previously, followed by a reflection or a sigma plane which is perpendicular to the rotation axis. Let us say if this is my rotation axis in a molecule, the sigma plane should be perpendicular to it. That would define you an improper axis, which is denoted by Sn. Let us look at a simple molecule which is the benzene again. So, here we know that we have a C6, that is I have a plane of benzene here, and I know that I have a C6 which is perpendicular to this. But once I have the C6, in order to see whether I have an Sn or not, I should put a reflection plane or I should put a sigma plane here. And if I put a sigma plane which is cutting through the atoms of the benzene, I indeed find that there is a sigma plane. So, that means I have a C6 followed by a sigma plane which is orthogonal to it. So, in the end I will have an S6 for benzene. And similarly, if you want to convince yourself of a slightly different atom, what we can do is we can take this cyclohexane derivative with X being a substituent, and what I will try and show you is that if I have this particular molecule, I am going to rotate by 90 degrees. Okay. So, for sake of convenience, let us number the atoms as 1, 2, 3, 4, and I am going to write down similar. So, I have my 1 here, so the substituent X would be here, 2, 3 and 4. So, if I go to 2, the substituent is down, and if I go to 3, the substituent is again up. So, I will write 3 here, and if I come to 4, the substituent is down, correct. So, now I have done a 90 degree rotation here. So, now what I will do is I will put a mirror plane here. So, if you put a mirror plane, what you would end up in is something like this. So, now this would become, and this will come here. So, I hope you can see that the one which I have drawn here initially, let us call this A, and the one which we have got by operating a 90 degree a 90 degree proper rotation followed by a mirror plane or sigma, and this is C4, I hope you can all see that, and followed by a sigma, I have ended up with exactly the same molecule here, that is on C1 I have the x which is pointing up and C2 the x is coming down and so on and so forth. So, in essence what I have is an S4 element of symmetry for this particular molecule. So, you must be wondering what is this got to do with chirality, or why is he trying to tell us about symmetry rather than about chirality. So, the reason why I am trying to talk to you about chirality and the symmetry is that a molecule is said to be chiral not only when it has 4 different substituents, but a molecule is said to be chiral in a more rigorous term if it has no SN or improper axis or improper elements of symmetry. So, only and only then a molecule is said to be chiral. But please do note that a chiral molecule can have a proper axis of symmetry, that does not forbid it from having any CNs, but that is not a necessary condition, it may or it may not have. So, if you just want to convince yourself, what I would encourage you to do is to actually go back and try to test out these two hypotheses which I have shown you, that S1 or improper axis with S1 improper axis of the first symmetry has actually equal to plane of symmetry, and S2 is nothing but an inversion symmetry. So, you can take a very simple molecule like ethane or the dichlorodibromethane I showed you in the previous slide to convince yourself of these two aspects, which actually embed both the plane of symmetry as well as the inversion into the improper axis, improper symmetry element. As a result, only one symmetry element, that is improper, is good enough to define whether a given molecule is chiral or not. With this we shall stop here. In the next lecture we shall go ahead and look at what are called as enantiomers and diastereomers. Thank you.